I'm going to give a quick talk on porting V8, JavaScript and WebAssembly runtime to PeerCap. So what is it? Like I said, it's a JavaScript and WebAssembly runtime. It has roughly 2 million lines of C++ code that is handwritten, and during the build, you will generate another 300 to 400,000. It's a crucial part of Chromium, NodeJS, Dino, Electron, Edge, Chromium Embedded Framework, and many other things. It has 6 JIT compilers and 1 ahead-of-time compiler, multiple allocators, and garbage collectors. And when you're building V8, you can build it either in a compressed pointer version or an uncompressed pointer version. As the name suggests, the uncompressed pointer version is the one where every pointer will be a capability, i.e. every JavaScript object will be represented as some kind of pointer, i.e. a capability. So that's the one we focus on because we hypothesize it will give us the most protection. Kind of like high-level overview, since July 2023 to July 2024, which is a 1-year span of where our fork starts, there were 19 critical memory safety vulnerabilities. So that's quite a bit for just JavaScript engine. And it's not just architecture-specific in code generation, but it also incorporates very strong assumptions about what is and is not a pointer, and it kind of conflates integers and pointers. So the issues we encountered during porting, they used an old Google style guide where in pointer t and in pointer t is kind of like a machine word. So we cannot really assume that something that is marked as an in pointer t or in pointer t will actually be a capability. And most of the time it is in fact not. It has ambiguous pointer provenance, so depending on the code path and the type, you might end up with your object field containing an offset and your offset field containing the actual object pointer. So this needs to be resolved. It assumes pretty much everything is packed. This is mostly for performance reasons, but that means things like torque, which is a DSL, have no concept of padding or like automatic alignment, so we had to have things like that. It assumes that in quite a few places that size of double is greater or equal to size of a pointer. This is quite painful when it comes to heap snapshots. And it, as I said earlier, it conflates pointers and integers, but not just in C++, it conflates them in its own compilers. This is quite painful to address. And there are many other smaller issues that we encountered along the way, but none quite as difficult as these ones. So what type of successes we had? We have managed to make an algorithm which is basically just graph tainting to propagate these notions of something is a capability, maybe is a capability, or is definitely not a capability throughout code stub assembler, which is what they usually use to implement things like JavaScript built-ins and various other things for high performance. So the way we do this in C++ is really just a const expr with a helper to say like, oh, this is definitely a capability, or this is maybe a capability, and then we just have some rules for those things. We're able to automate most of the alignment requirements in torque by just small changes to the compiler. This was not too bad, but it does have some code changes, unfortunately. And we are able to handle, as a result of all of this, a good amount of JavaScript on real-world websites. There was a demo plan, but we don't have internet, so a demo visiting a real-world website without internet is not really going to work. And most of the work was done over the past roughly 6 months with one staff year, or one staff member rather, which is really not a lot of work when you consider that V8 is pretty large and has all of these things. In comparison, the Chromium security team has over 100 staff members just for security things. So what does this kind of like look like? As I said, we won't go through this in detail, but on the bottom we have torque, which is a DSL to kind of implement JavaScript built-ins, similar to TypeScript, but not really. There we just kind of like did minor changes. That generates CSA, which is code stub assembler, which is the thing that's actually used to implement all of these things. So this is a C++ DSL. And in there, we do all of this graph tainting and type inference and all of these things. That feeds into Turbofan, which is an optimizing compiler. That actually compiles our built-ins along with the interpreter. On top of that, the parser required no changes. The interpreter required very minor changes, so the CSA stuff automates most of it away. There's another JIT compiler, Sparkplug, that is a single-pass JIT compiler. Again, minor changes there. Turbofan is, even though it's used as a head-of-time compiler for built-ins, it's also used as a JIT compiler. There we had to kind of modify some compiler passes to be aware of what is a capability and so on. We had to build a new backend to generate capability instructions. That was not too bad. And obviously there's a line there that says deoptimize, which we had to kind of make the stacks between the interpreter and the JIT code align, which required some changes. So what does this look like kind of in lines of code? The way this is calculated is we took the commit before RISC-V and the commit before Morello and kind of just like calculated the lines of code. So for a RISC-V backend, it seems that all you really need to do is add platform-specific code, modify a couple of tests, namely platform-specific ones, and add a couple of things behind if-defs in generic code. So not a lot. For Morello, though, it looks a little bit different. So we have fewer lines of code change, but that's because we did not add new tests like RISC-V did, so it's comparable. A lot of that is in platform-specific code and tests, but we did have to modify compiler passes, we had to modify CSA, we had to modify allocators, garbage collectors, and then various other things that we ran into, along with this little thing says torque, which is the DSL. This includes both the compiler changes and the changes we had to make to torque sources itself. These are the test results. I won't go over them right now. Slides will be available. The limitations, we haven't done WebAssembly yet. And we currently only support uncompressed pointers. It's probably not that far from actually working, like fully working. We're passing like largely, like 90% of the test suite is passing. We don't have support for maglev, which is another JIT, and that is just because our baseline commit did not support maglev for uncompressed pointers. It was added like a month later. It doesn't work well enough to handle NodeJS's snapshotting process because NodeJS adds quite a bit of things. And it's a version from July 2023, so we need to pull it forward. Future directions, the plan is to tighten JavaScript, bounds on JavaScript objects, and add WebAssembly support. Particularly, the interesting thing here might be to kind of optimize how memory 64 works by not requiring all the manual checks before it loads and stores, like it is required today. Add support for pointer compression so that we can evaluate how much overhead is added with each one. Add maglev support, since we do want this JIT. And just generally merging forward to the latest versions of V8. We obviously want to support Node.js and Dino, which is the runtimes that most people use. And obviously, we would like to add CHERI RISC-V support. And currently, it is unclear to me how mature the baseline RISC-V support is in V8. It seems to be maintained, but sometimes gets left behind. And that's it. I'm a little bit early, so I'll take any questions.